It's equal to 0 if n is...
Okay, it is 1, so I think we'll get started. If talking about math phys isn't that interesting. All right, well, thank you for coming. There is no obligation, so I appreciate it. I've written the title up there because I'd forgotten it. So importantly, I also wrote like the 2 references that I used for this whole thing. So if I say something incorrect, the correct statement is going to be either in Rourke and Sanderson or Skorpan, the first chapter. Don't have to read the whole book. Yeah, okay. The way I'm going to do this is backwards to the way I wrote the abstract. I'm going to actually introduce, quote unquote, the simple objects, and then we'll take like a sharp turn and go, what is an extremal use case of this stuff? And it will not be obvious how you get to there from the stuff we talk about, but there is a purpose, and that's what I'm trying to convince you of. Hello. Okay, so the whole thing here is piecewise linear. So we need to make sense of what we mean by linear. And so we're going to do a very Bourbaki approach and run with definitions a lot, where by linear, we're actually always going to mean affinely linear. So we don't have a direct notion of 0, right? So then we have a linear subspace, which I'll just say subspace because I'm a good mathematician and hence lazy. Is going to be a translated vector space, of course, right? And then a map, let's go from Rn to Rm. Do let me know if you can't see, because I will endeavor to write larger, is going to be linear if, and this is going to be a theme throughout these, the minutiae are really important, and so we're going to get stuck with indices and taking care of all these tiny little details. So we're going to have a collection of, thankfully, real numbers, such that they sum to 1. And then we're going to have a collection of vectors in Rn. And then, so with these, what we want to have is that f of the sum is going to be affinely linear in this sense. So we have the sum right? Importantly, this isn't linear. This is affinely linear. So you cannot like get 0 out of this. F of 0 is not 0, importantly. All right, and so whenever I'm going to say linear, I'm going to mean linear in this sense. All right, and then another definition, get biscuits.
So is every linear map, is it a composition of the traditional linear map and a
translation? Yeah, exactly that. All right, for any 2, they don't even have to be subsets, they can be subspaces of Rn. We're going to define the join it's going to be the convex combination of these 2 guys. The lines between the 2 sets, exactly. So a really simple example is if I have this line as A and these 2 dots as B, then I'm going to take all the lines that go emanate this way. So then this thing is going to be AB. Yes?
Quick question, do we impose that lambda is at most 1?
Yes, we should also do that. Yes. There we go.
What about your definition of like a linear function, where you provide the lambda I source to be non-negative?
Yes. Yes. Okay.
And it's always been closed, right?
Pardon?
It's always been closed, right?
Closed in what sense?
Logically, because provided the MBO closed.
Yeah, I think so.
A and B are equal and M are
I said, yeah, if the MBO closed.
If A and B are closed. Yeah, I guess so. Yeah.
Are the quantifications that were says lambda in A existential or universal? Is this for all lambdas A's or is this for some lambdas, some A's? In the first definition.
Like here.
On the left. At the bottom.
Yeah.
Yeah, for all.
For all. Yeah. Okay, so we have joins, and then from joins, a necessary remark, if A is the empty set, of course, their join is just going to be trivial, right? So there's some notion of this being a binary operation, yada, yada, yada. But that's not the point. Pardon?
Is it not the answer? Because there's no A.
No, we define the problem away.
I see.
Yeah.
Natural.
Okay. Another definition, it's going to be lots of definitions in the beginning half. So obviously, we're going to be lazy again, and we're going to denote the singleton set just by the element in the singleton set. And so we're going to say that little ab is a cone with vertex A and base B if each point not equal to A has, is uniquely expressed as a convex combination. Obviously B and B and lambda and 0 to 1. So to really see the point of this definition, if I have sort of a semicircle looking thing and my point, call this A, this is B1, this guy who looks like a cone is in fact a cone. But if I have my little point and say a circle, these multiple intersections, call this one B2, this A, this guy isn't a cone, right? Because we intersect twice. We're not uniquely expressed as a convex combination. Yeah. Yes, I don't know who had the hand first.
That picture with B2 that you've got is drawn in the plane and not,
Drawn in the plane,
not
yes.
as my eyes have seen.
No. Yeah. Yes.
Thank you.
All right. And now, finally, we can get to sort of the main-ish objects, where we're going to say a subset P of Rn is going to be a polyhedron if each point in our polyhedron, or subset, has a cone neighborhood which will denote NAL. This isn't a massive requirement. The requirement, however, that L is compact is. I guess it should be a such that to make sense. Then we call n a star and L a link. So n for star. All right, and then these are going to be like sort of the main objects at play. Well, I mean, there's one. Pardon?
We filled it or not filled it? Both work.
L must be the boundary.
I think, yeah.
And A is the point inside.
Yeah. So some examples. We'll come over here. Some more less maybe tangible examples. Oh.
And do we require this P to be dimensional in any way, or is it just?
No. Can be any dimensional, which is important. Okay, so obviously Rn and subspaces of Rn are polyhedra.
Actually, question. Sorry.
Yeah, no, please interrupt me.
Cone neighborhood, you mean it must be a neighborhood?
Yes.
Interior container.
Yeah.
So it must be n-dimensional in some sense.
Oh, you mean the cone neighborhood has to be n-dimensional? Yeah.
They would have the subspace, right? So it's be
So if P is two-dimensional, then we think, under the subspace closure of P.
subspace, right? You can have like this square embedded in like R3. Would be a polyhedron.
If P is this square, yeah, right?
Yeah.
I think so,
So this-
if I understand your question.
I was just going to say, so this cone neighborhood, is it open? No, it shouldn't be. Because
Yeah, no, in
so
fact.
we just mean a cone that contains a point.
Or cone that contains an
Yeah,
So
In
the
that sense.
interior contains the point.
yes. It's a funky definition slightly. Yeah.
So for this example, is the proof just, you take the point and then you do like a disk around containing that point?
Yeah, I think so.
But just to be clear, it depends on the space P, right? If the space P is two-dimensional disk in R3, then the two-dimensional square is a neighborhood. Whereas if it was P was three-dimensional, then the square would not be a neighborhood anymore because it's back in intersecting.
Yeah, I think so. Yes. Yes.
So P matters. So the shape of P.
I mean, yes, P matters. Yes. Yeah. Okay. Where am I going with this? There's a bunch of other examples. I'll just say them. I don't think I'll write them. But open subsets of polyhedra, open in the subset topology, are also polyhedra. Intersection of finitely many polyhedra is a polyhedron. Finite products of polyhedrons are polyhedrons. Polyhedra are polyhedra. Anyway. And also arbitrarily locally finite unions of compact polyhedra are polyhedra. Fun fact. Yes?
Can you give a non-example?
Yes, that was my next thing. After one more example, that will be very operative. Cubes. Cubes are going to be the whole shtick in the later half.
So one question.
Yeah.
Here you mean open the first star, you mean open subspaces, right? Because
Linear subspaces in the sense of the initial definition.
okay, so
Yeah, or affinely linear subspaces. Take your favorite n-dimensional vector, then take your favorite epsilon, is a polyhedron. Right. Called a cube, because it looks kind of like a cube. Importantly, Rourke and Sanderson define what they call their unit cube, and there's a distinction to be made here, in minus 1 to 1, and folded many times. They make the distinction that for n equals 1, this is not the interval 0, 1. Right, so I1 is different from I. But I won't use this notation. I'll use just the interval. Oh, I guess really just not equal to.
Like, sorry, is this because you have -1 and 1? Is that why?
Yeah. So like if you see I1 or just I, it's not the interval. It'll be the cube. Is that, yeah?
Sorry, so the L in the cube, is it just going to be the boundary of the cube?
I think so. Yeah. These guys are going to play the role of spheres and balls in the PL setting. Yes.
On that remark of boundary of the cube, if I take a point on the boundary of my cube, it's not going to be a cone, right? Because it's not unique anymore. Because through my plane, I can take a bunch of different ways to get there.
L is not.
It's technically it's the edges, not the faces, right? That side. So if you take out the full boundary of the cube, that doesn't work. There's many parts. But if you then take only the edges. Oh, I see what you're saying. Yes.
Which L can change.
Yeah.
So can you not still take a point on the edge?
And just get that in the same depth of that.
Yeah.
Does it make sense? Okay, cool. Thank you. Okay, so non-examples. This guy and this guy. So this one doesn't have a cone neighborhood, just the circle by itself. Right, because it's, yeah. And then the square with a tail has a cone neighborhood, but the L isn't compact in that cone neighborhood. Why? Because if the tail, you can like run away on the tail. No, like you're not the interior there.
What I'm saying, you can actually put that A can't be inside of the column. Is that also a counterexample?
That's not what the book said. I'm going to be honest. That's not what the book said. The book said it has a cone neighborhood, but the link isn't compact, which is the requirement we have.
Is there a quick way to see that the circle is that of region?
Not off the top of my head.
I know you just take like any possible element and crank through it, and then it still goes outside the circle.
Yeah, I guess. Yeah.
Sorry.
Like take this example actually, right? Any cone through it is actually not a cone. A cone-like construction. You don't have the unique expression.
Can you motivate like why this is the right definition for a polyhedron?
Yeah.
A circle should be a polyhedron. No? Okay.
Yeah, I think it's an abstraction in some sense of just made of linear straight lines, and I mean at best a circle is an infinitely. Yeah. Yeah.
Can I ask about another example?
I don't have another one.
I'd like ask you about it.
Oh, yeah, sure.
Imagine this soccer ball. After the soccer
Sure.
ball, there's a bunch of hexagons,
Yeah.
right? If I pick an edge, like a vertex, sorry, of that, then I can pick the edges of any of, like, if I have these faces. these edges that don't touch that vertex, pick those. That becomes a cone neighborhood, right?
Potentially, yeah.
A cube. Pick a point. A
Yeah.
boundary, and then look at any edge that isn't touching it directly. Second order away.
Yes,
That becomes neighborhood, right?
I think so. Okay. Okay. So with this, then the next definition we need, lots of definitions, is going to be a map between polyhedra. And we want this one, this is where we finally introduce piecewise linear. So and I'm just going to call it PL because I don't want to write piecewise linear every single time. If each point in our domain has a star,
So star is a compact.
a star is one of these guys. Yeah, compact cone. That's what we said? Yes, yes. And this isn't immediately clear that this is piecewise, right? Like, it's not. But I'll give some examples, abstract examples, I guess, but examples. Of course, a linear map, we should really hope, is PL. The restriction of the linear map from Rn to Rm is PL, yes?
Is a map, such a map continuous necessarily?
I think so, yes. Yes.
You need to restrict to a polyhedron, right?
Which one?
The restriction of the linear map.
Yeah, restricted to a polyhedron. Yes, 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 yes. Thank you. And if we take over some index a locally finite of a polyhedron, then a map to any other polyhedron is PL if and only if it is PL for each P alpha. And then this sort of, we can formalize further and get the notion that it's PL if and only if it is, quote, linear in pieces. Yes, before.
Is it implicit in the assumption that we want the image of the restriction to be polyhedra? That's maybe not a point.
There's a exercise in Rourke and Sanderson that talks about like the image of a compact polyhedron is a polyhedron under a PL map.
Is compactness required for that?
I think so. There's probably ways you can extend it to non-compact polyhedra, but I don't know of that one.
It probably is required.
Close to the right. I think close to the definition. If you have like a weighting something and they are mapping back into the something. Is that right? When you do that stuff.
That literally is compact by definition, so close stuff.
Question.
Yes.
The definition of PL map, is it basically saying like the image of a line is a line?
Yeah, it's locally conical. Yeah. All right. Okay, so we've introduced a lot of the key players. 2 more, I promise. And then we will do the hard pivot to Millennium Problems. So this last little bit is to motivate sort of the forthcoming computational topology talks, where they're going to be talking a lot about triangulations. So we need to figure out what that is. And to do that, we need simplicial complices. So to that end, I'm going to take a finite set of vectors and we're going to call them independent if is linearly independent. Right, so this is sometimes also called like affinely linearly independent. I equals 1. I even wrote 1 and then I changed it. I equals 1, yes. So then a K-simplex in Rn is the repeated join of K plus 1 independent vectors. Important note, it can be shown that join is associative and commutative, so this is well defined in some sense. Join, where we take the convex combination of 2 subsets. Yeah. So we're going to call the VI's vertices, and then a simplex spanned by a subset of vertices is a face, which we're going to denote in this way. So B is a subset, is a face of C. Right? You can put some ordering on it and do shenanigans that way as well. So a simplex is a compact polyhedron inductively, because you can take the cone on K-1 simplices. Right? And then from here we can also define, I think there's enough space to squeeze it in. A simplicial complex.
Maybe draw like one.
Draw one. I mean, it's a triangle, simply, or in think. Oh, well, you can have it just a triangle. You can have the filled-in triangle. Which one? Yes, you're right. Or you could have the 3-dimensional. Can I draw a 3-dimensional one? We'll find out.
What is the 1D1 or the 2 simplex? What about the 1D1 and the 2D1?
Like the line and the point, sure. Yes, that's fair.
In the 3D one,
Yes.
line, you declare that to be a face.
Yes, the line is a face. Yeah.
Also points are faces, is that right?
Points are faces, yes, because they are spanned by the one vertex. Okay, so a simplicial complex is a finite collection of simplices satisfying one. We want if C is in our complex and B is a face of C, then B should also be in the complex. And 2, if B and C are in our complex, then the intersection of these two is a face of both B and C. And then so these simplicial complices are important.
There's about the embedding, right?
Pardon?
The section there is one set embedded into Rn, right? Because oh, you have an Rn.
Yeah, these all live in Rn. I'm not worrying about abstract simplicial complices. And the underlying polyhedron, which is the last little bit, will denote that way. It's just the union. All simplices. Okay. Yes? I don't think so. Why? They can be? They can be. There you go. They can be. Yes. No, wait. Yes, of course. Yes. I'm lying. Sorry. Yes. Yeah. That's where we'll get into it. That's the last little bit. So, okay. Jumping all the way on this side.
Sorry, one.
Yeah.
Is the empty set of face?
Spanned by no vertices. I think so.
Wait, how can you be independent?
Yeah, it is.
Yes.
Yeah. It's a, yeah. What are we doing for time? Okay. All right. Finally, a triangulation. Was stated for a compact polyhedron, but it can be extended. It is going to be a pair, KT, where K is a simplicial complex, obviously. And T is a map from the underlying polyhedron to our P. And that's going to be a PL homeomorphism. And then so out of this, we can extend these definitions pretty naturally. Yes? Bijective PL both ways. Yeah. Thanks. Yes. Yes.
So it said that square of the line is not a polyhedron line.
The square with the line? Yes.
Yeah, well, I can easily map that to the underlying polyhedron of a simplicial complex. So is that so the definition of the underlying polyhedron equal to the definition of the polyhedron?
No, it's fine.
Is that not the underlying polyhedron of a simplicial complex that not is ever there?
And the point. They're all going towards the point on outside.
Yeah. I need to check the book because I'm not sure. They give it as an explicit non-example, so I'm not sure. I should have checked the details. That's. If it's which I assume must now be the case. That wasn't made clear. That was my apologies.
It is a feature complex, it's not open. It's open now, but it's closed.
Okay, so importantly, two theorems, one by Rado in 1924, if I'm correct. Yes, every two-dimensional manifold has a triangulation. And then, so that was 1924. In 1952, quite a while away, Moisey says that every three-manifold has a triangulation. A topological, which makes it hard to prove. And hence the big gap. And it's part of the reason then as a corollary that we can then go and say that every topological manifold has a PL structure, which then has a smooth structure, yada, yada, yada. This is a big stepping stone in that. Oh, I mean, no, 1D is trivial. So I didn't put it up.
You don't want to go through these zones, but how did you go from like polyhedron to the manifold?
That will be made clear next, because the next thing is a little, what I've titled in my notes, recollection on manifolds. So don't want to assume that everybody knows necessarily what a manifold is. Importantly, so you take your favorite manifold-looking thing, which has holes, of course, and you take a point inside, right? And we have open neighborhoods that beam us out in two ways into different open neighborhoods. This is Rn, of course, and another Rn that maybe looks a little different. It's fine. Call this phi and c, and then we have a transition function, right? Which we'll call phi c inverse, because these charts, they're like homeomorphisms, they're bijective, they're invertible. Yeah. On the intersection, yeah, we have these transition functions. Yeah, phi and then psi. Did I? Backwards? My arrows are the other way around, yeah. There we go. That should be fine.
What sort of manifold did you say you were defining?
This is just a manifold in general, right? We have charts beaming down.
Okay, so I don't think you need to talk about the transition functions then. That's just like a smoothness thing, right?
Well, if we require them to be continuous, then this is just a manifold. If we require them to be PL, then that's a PL structure on our manifold, and we get PL manifolds. And if we require them to be smooth, we get smooth manifolds, because that's a smooth structure. Yeah. And other topological considerations, but like, yes, yeah, axiomatically.
So we're probably embedded here, right? Because of these theorems, because we're going to define like polyhedron over Rn.
Well, no. So extending this definition to make sense. So basically, a triangulation amounts to having a PL structure.
And that's what those theorems are referring to.
That's what these theorems are referring to.
Right, because it currently doesn't make sense under our current
Yes, under our current definition, does make sense. Yes, I agree. So importantly, we get continuous. If I can spell, will give us a category of manifolds, what we're going to call top, because topological manifolds. That's the convention. PL maps are going to give us the PL category of manifolds, and smooth maps are going to give us the smooth category called diff for differentiable. Okay.
So to be clear, sorry.
Yeah.
In those theorems, are they genuine triangulations or are they just PL?
You can convert one to the other.
So you're saying in those, in 2D and 3D, PL is only triangulizable?
What did you say? Is it not?
In 2D and 3D, is PL if and only if the PL manifold, is that equivalent to being triangulizable?
I think so. Yeah.
So that is general, right?
Okay. And with this, we can now actually get into the Millennium Problem, sort of. So the conjecture, it's actually the generalized Poincaré conjecture. And we will be clear why it's generalized. We're going to let cat be either top, PL, or diff. And then the claim is every n-dimensional cat homotopy sphere is cat isomorphic. So isomorphic in the requisite category to the n-dimensional sphere, Sn. So the original conjecture is in 1904 by Poincaré in dimension 3. That was only proven in 2003 by Perelman. Is the question? Yeah. Compact, closed manifold, so compact without boundary, homotopic to a sphere. No, it is category, like a cat sphere that is a homotopy sphere. So it is either a topological homotopy sphere or a PL homotopy sphere. Pardon?
Can you just write out the whole definition of what a cat homotopy sphere is? Maybe a bit easier.
Is a closed n-dimensional cat manifold that has
homotopy type
of a sphere.
So homotopy here is like close cells?
Yeah.
Purely.
Yeah. Yeah.
Are we saying that the sphere is an object in all three of these categories?
No, the topological sphere.
Also, just like
Yes. Yeah. Okay. A couple of remarks on this. Is there a question? Maybe?
Actually, just to clarify, when
Yes.
you say closed, you mean like back without boundary, right?
Yes, exactly. I won't write them. It turns out this is true in top for all n. This was a big thing. The hard proof is, well, in dimension 3, it was the last one. And in dimension 4 was proved by Friedman in 82, but it was only fully formalized in, I mean, technically the book was published in 2021 with Aronimo Ray, who was here like months ago, was one of the main authors there in that endeavor. It is also true in PL for all n but 4, because 4 is still open and we don't know. What we're going to prove is for dimensions greater than 6, because the 5th dimension, both books say is really technical and do not go into any detail. So, but I think the argument is similar-ish. And it's generally false in diff. So first counterexample was Milnor in dimension 7 is a Milnor sphere that is an exotic structure that isn't. Like you get homotopic to the sphere, or homotopically equivalent to the sphere.
Forget the structure, like topological structure.
Yeah, you're assuming I know what topological homotopy means.
You can continuously deform it to the sphere.
All right, cool.
This is not in both directions such that the composite is homotopic to the infinity map.
Anyone wants to
So you're going to be talking about PL?
It's like
Yes.
homomorphic,
So-
but it's still kind of the same thing. Imagine, I don't know, like this is homotopic to a point, because you can squeeze it into a point, obviously not homomorphic. I think it doesn't know the homotopy.
No,
The
yeah,
homotopy
I don't
was
know.
homotopy was the problem.
Yeah.
They kept answering the homotopy.
So is it also true in top?
It's true for all n in top.
But not for Z?
Decidedly not for diff. Yeah.
You want something
Um,
that's not the second morphic to a sphere, or the truest homomorphic, but it's the next closest thing to a sphere, homotopic to a sphere. Okay? Very, very similar. They want to show that it's so similar that it must be a sphere.
As a fun fact, I have written down here the dimensions which it is true for diff is 1, 2, 3, 5, 6, 12, 56, and 61. Naturally.
Remaining numbers disproven or unresolved.
Yes. I'm not sure. I think, and a lot of them is disproven, especially where you have the curve and Milnor spheres, the exotic structures, but and known is not known. All right. Okay. In the interest of time, I'm gonna state a lemma without proof. If we have PL n balls, B prime, and H a PL homeomorphism of the boundaries, then we can extend H to a homeomorphism B to B prime. PL homeomorphism. Right? The cube. It's not there anymore. The unit cube. And then the sphere will then be the boundary of the unit cube, the n+1 unit cube. Okay. Finally, we introduce a cobordism. So a cobordism is a triple which is it's going to be a compact manifold W such that its boundary is the disjoint union of two other one-dimensionless manifolds. This by itself won't be enough for what we want. What we want actually is H cobordism. So if the inclusions are homotopy equivalences, then we call it an H cobordism. All right, and this construction will help us then prove it for dimension greater than or equal to 6 by using an absolute hammer. I did promise a hammer, so we will state it here. What are we doing for time? Ooh, no, great. Okay. This is the proverbial H cobordism theorem. The proof of this is a thesis in itself. So I won't prove it. It's by Smale in 1961. It almost immediately implies the generalized Poincaré solution, Poincaré conjecture. So it says, you suppose W-dimensional manifold is simply connected H cobordism.
Are we still in the PR category?
In the PR category. Yeah, so is A simply a connected H cobordism with W greater than or equal to 6? Like, yes, yeah, well, no, W itself is simply connected.
You don't think also M0 and 1 for it to be a H cobordism? We're missing the couple that we have.
Yeah, I mean, shortening the notation. If the M0 and M1 are, yeah.
Is there a picture for cobordism?
Yeah. One of these guys. One of these guys. This is my M0. This is my M1. This is my W. W can have holes, technically. Perfectly fine. That's of a cobordism. You mean of an H cobordism? I think that one works also. Without the hole. All right. Yeah. Okay. Then the theorem says. I knew that. We have W is PL isomorphic to M0 times the interval, which implies that M0 is PL isomorphic to M1. And then from here, in the interest of time, I won't go through the proof of the Poincaré conjecture. I do have it here, so if you have questions, I have it here. I'm free, we can talk about it. The idea is you cook up an H cobordism inside of your homotopy sphere that will then reduce to simply this. And the answer will just sort of pop out immediately after whacking it with this lemma twice, because we want to extend to boundaries, and then boundaries are boundaries because of the way we construct our spheres and balls. Yeah, Smale got a Fields Medal for this in the year that they gave out Fields Medals, because it is a weapon of the theorem. But yeah, okay, we might call it there because people have places to be. Thanks.
Could you give a brief explanation of the lemma?
Oh, yeah, that one is super chill. I mean, we can assume that B is B prime is just our n cube. And then we are going to define big H of lambda x to be lambda, where is it? Little h of x. For x in the boundary of IN, and this usual lambda. And then we know that this is the cone construction on this guy. It's really just this. Yes?
This construction specifically saying we can extend a homeomorphism of the boundary to a cube. Like, that's the
Yeah, a PL homeomorphism of.
like a specific one, because like they will be homomorphic if they're IN already, right?
So this is the point where all of this falls for two, because this is the thing that's called the Alexander trait, where you have something on a sphere, you want to extend it to the ball, and you do this like this, and what happens in the center is not. So you go to the center.
Look exactly what this is writing, right? You are extending by squeezing what you have in the boundary around the rays.
Oh, sorry.
But then it takes the business at the center.
Yeah.
So I guess the.
B prime aren't always the cube. Okay. I thought this interpretation like that. Okay.
So little h something like that.
I just got confused because I thought you were saying that we always split the whole cube. What do you think?
Say again?
Oh, we wrote B equals.
You can assume it to be, right? Because we take them. Oh, these two are. So it might as well be the PL isomorphic too. Sure.
How do you know the isomorphic?
By assumption.
Doesn't that also imply that the boundaries are pure isomorphic then? And then so you're assuming the Poincaré conjecture, the Poincaré conjecture?
Actually, it's a specific homomorphism, or a specific H.
They're not homotopy.
If they're homomorphic, then the boundaries are
So we're talking about
boundaries not boundaries.
Yes.
Then that is that.
because you have to fix a particular H, those like what's on the boundary imply. But because it's like it's an extension idea. Because you're not taking like the canonical. Yeah, that's.
I think the next class is going to be working.
Yeah, we should. But I'll be outside the chat, so it's.